Hey guys, so second video of the year. I'm going to go ahead and start talking about the international systems of units and the units that we use in chemistry. Last year, you used a little bit of the units, but this year really we're going to focus on using those units a lot more, especially in the lab, because when we measure things out, it's really, really good to know what you're converting to and from. Because I may give you something in, and this is for the future, but I may give you something in grams as a solid, and I want you to make a solution, and you need to know how much of something you need compared to how much water. I've done these things in the lab before, so it's not like it's brand new, but I want to make sure that you know how to do it. So again, this is all on the International Systems of Units, also known as the SI units. After this video, you should be able to identify the 7 base units, know metric prefixes, convert between Celsius and Kelvin, which actually you're not going to be doing that in this video. You'll do that in the next video, converting, and then distinguish between mass and weight. All right, so let's go ahead and jump into it. The first thing I'm going to ask you is, and I want you to just think about this, do you know the difference between the metric system and the English system? So when I say English system, I mean like inches, feet, ounces, the things that we use here in our country. What is the difference between that and the metric system? So I'll let you think about that. And while you're thinking about that, I'm going to go ahead and start talking about measurement and how we measure in science, more particularly in chemistry. I want to go ahead and talk about the English system. It is never used in science. You will never measure anything in inches. I will make sure that you, when you're reading a ruler or reading a meter stick, you are always using meters, centimeters, whatever the case may be, but you're never using inches. And the reason for that, I'm going to answer that question that I asked you at the beginning. The English system is really confusing. Some of you probably have those things memorized just because you've been in shop classes, and that's just something we use standardly here in the United States. But in science, we don't use that because it's actually a lot harder to convert. And there's actually been like huge catastrophic things that have happened because of the fact that America uses the English system. And that happened actually, I don't remember what year it was, but the calculations that were done in America were done using the English system, which seems kind of crazy, but then they weren't converted, when they were converted for another country to use the same kind of project, there was no conversion. The units were changed, but the actual conversions of the numbers weren't changed. So for example, 3 inches does not equal 3 centimeters. So it's actually really confusing. We just don't do it in chemistry or in science at all. The metric system is used because it is super, super handy at converting between different units when we talk about the prefixes. And I'll get to that here in a second. Some things I want you to understand is that measurement is a quantity that includes both a number and a unit. So if I were to say to you 12, you have no idea what I'm referencing when I say 12. If I said 12 meters, now you kind of have an understanding, oh, maybe she's measuring a football field, or maybe she's measuring something really large. 12 meters is pretty large. If I were to say 12 centimeters, that's a lot smaller. So maybe I'm measuring the palm of my hand, or I'm measuring just a shorter distance. So the coefficient or the number and the unit really help you provide a value to whatever it is you're talking about. So this leads me back into the idea of the SI base units. Metric system is super convenient because it uses multiples of 10. So if I were to say 10 centimeters, you could easily convert 10 centimeters to 10 meters or 10 centimeters to 10 decameters, whatever the case may be. Now, it's probably not wise to convert 10 centimeters to 10 meters, but we'll get there. The International Systems of Units is a system of measurement based on the metric system. So basically what I'm telling you is that all of science and all of the science community uses the International Systems of Units, also known as the SI units. I am going to be providing 2 tables to you. The first one you see on your screen right now, and on the next slide, I'm going to talk about those things. You do not need to write these tables down. I will give these tables to you when I talk to you about this in class. Do not write these tables down. I'm going to go ahead and talk to you about the base units that we use in chemistry, more particularly these first 5 that we see. So length, mass, temperature, time, and the amount of a substance. So length is always measured in meters, and you're going to find that that's really inconvenient if you're trying to measure in the meter. Or if you're trying to measure like a penny, right? Measuring a penny using a meter is really hard to do. So we actually have this really convenient way of converting down and up from the base unit. When I say base unit, I mean that there is no prefix in front of this thing. So a meter is one thing, and there's no prefix to tell me that a value of that. And I'll show you that here on the next slide. The kilogram, now you'll notice that this base unit has an actual prefix. So kilo it stands for 1,000, and the symbol for that is kg. When we do our masses, I will tell you that most of the time I'll just say do everything in grams. It's just more convenient to do so. Temperature is done in Kelvin, time is always done in seconds, and the amount of a substance is known as mole. And we will talk about mole day in next month. It's coming up, October 23rd. Write it on your calendars. But anyway, SI uses what's known as prefixes, and I'm going to go ahead and slide over to the next slide. Here we go. These prefixes help distinguish between units of different sizes. So for example, I'm going to go ahead and start drawing on here. For example, I have the centimeter. So centi stands for 1/100th of a meter. Okay, so if you go back and remember our base unit for length, and I'm using length as my example here. Our base unit for length is the meter. So you notice here, the meter is just 1. The meaning is 1. So 10 to the 0 equals 1. If you go down away from the, I can't think right now, sorry, from the base unit, you are going to notice that these numbers go towards the negative. That means they are smaller than 1. Any negative exponent is smaller than 1. So deci automatically means you are after the decimal. And I'm going to do this in class. I will spend a lot of time doing this in class. So please don't freak out just yet. If you go above or higher than 1 on this particular chart, you are going to notice that these numbers get larger than 1. So a decameter is of the value of 10. So 10 is obviously larger than 1. So we'll have 1 decameter equals 10 meters. Same thing for hecto. Kilo is the more popular one. You are deviating away from the base unit 3 times. That means that 1 kilometer equals 1,000 meters. And we're going to do all of these conversions in class because this can get a little frustrating if you let it get out of hand. So we will practice this. Don't worry. All right, so hopefully that's not super confusing. But if that's confusing, let's go ahead and go to another concept that may get really confusing as well. This is what's known as the scientific notation. And scientific notation is a tool used when numbers are too large or too small. So it's really, really inconvenient to say and write these two numbers here. 0.00000000911. I don't even know if I said enough zeros. That's a really small number. I know it's a really small number because all of those zeros are after the decimal point. And then we have 9100000. That's a really large number because all of the zeros are before the decimal point. If you don't know this already, the decimal for this really large number is right at the end. Oops, that didn't really work out. But right there at the end. So we don't usually write the decimal at the end of numbers because it's unnecessary. You really only write the decimal before a number if it's smaller than 1. So a decimal before any numbers indicates you have something smaller than 1. When you're talking about scientific notation, you're always going to have a coefficient and a 10 raised to a power. And so what I mean by that is that like these guys here, we have coefficient 9.11, and typically you're going to see it in 3 digits. When we talk about significant numbers and what that means, like significant digits, you'll see that maybe we won't always have 3 coefficients. But in this case right now, I just want you to know you have 3-digit number followed by a 10 exponent. And like I said, if you have an exponent that is a negative, that means it's a really small number. If you have an exponent that's a positive, that means a really large number. Large numbers will have lots of zeros before the decimal. Small numbers will have lots of zeros after the decimal. I already said those 2 things. So I'm going to kind of try and show you right now how we would convert these things. like I've already done the conversions for you. So this small number here is this small number written in scientific notation. So notice I have taken out all of those zeros and I've just made it into a nicer version saying 10 to the negative 28. If I wanted to write all the zeros, then I would just have to add 28 zeros to the end of the number. If I had this really big number here and I wanted to write it in scientific notation, I would move my decimal all the way until it's in between the first two non-zero digits. So I would just count 1, 2, 3, and I know that that looks really bad because I don't have enough space. But you would count all the way until you get to in between, and then however many humps you counted, that's how much goes after the decimal, or excuse me, goes after the 10 for the exponent. Same thing goes for the very large number. I have my decimal here at the end. I will just move it and continue to move it until I am in between the first two non-zero digits, and then I would add the 10 to the whatever exponent, and in this case, it's 10 to the 15. That seems really confusing, but I'm going to go ahead and do a smaller one. So let's say I have 13,674. Or you know what? We're going to go ahead and change that to 13,600. That makes things a little bit easier. I'm just going to erase it and show you again. I don't even know where my eraser is anymore. They moved everything on me. Okay, sorry. Okay, so let's say, again, I have 13,000. And for some reason, I just don't want to write 13,000. It seems annoying to me. Don't forget your decimals at the end here. I'm going to write 13,000 in scientific notation. So my decimal's here. We don't typically write it, but it's there. I'm going to move my decimal until it's between the very first non-zero digits. So if this was 13,400, and I can show you that example next, you'll see that as you're moving your decimal, the first two non-zero digits are 3 and 0, but we want between the first two non-zero digit numbers that start the number. So I'm going to show you this. I think I'm just confusing you even more, and you're just like, what the heck? But anyway, so here's my decimal, 1, 2, 3, 4. So that means I have 1.30 times 10 to the positive 4. I know it's a positive 4 because this is a big number, a very large number. Let's see here, and I'm going to erase this, and I'm going to show you if I had, let's say I had 13,400. 13,400. Again, my decimal's right here. I would just move it 1, 2, 3, and 4. 1.34 times 10 to the 4th. That's how you'd write that in scientific notation. Same idea for really small numbers, but now we're just going in the opposite direction. So if I had 0.13400, the big difference here is that the point or the decimal is now at the beginning of the number instead of the end. So I'm going to move this decimal until it's between the first two non-zero digits. 1. So 1.34 times 10 to the negative 1. Does that make sense? Hopefully. No? You're just like, what? Okay, let's do that again. I'm going to do this now with a lot of zeros. Sometimes that's easier to visualize. All right, so I have 0.0000467. That look like a 6? Hopefully. All right, so again, the decimal point is the very beginning, and there are a lot of zeros that follow. Let's move this decimal. 1, 2, 3, 4, and 5. So now I have 4.67 times 10 to the negative 5. Move my decimal place 5 times, but I have moved it in the opposite direction. There are a lot of zeros there. That would indicate a small number to the negatives. Hopefully that makes sense. We will practice this in class, so don't freak out right now if you don't get it. We will spend at least a day or two on this alone. All right, let's talk about units in chemistry. In my notes, you'll notice that I have added temperature to this. I forgot to add it to this slide, and I'm not sure why, but you'll see that in the notes. So length is always measured in meters. So if I were to tell you to measure a penny, the unit that we use in chemistry is the meter. So you're probably going to measure in the centimeter first, and then you would have to convert that centimeter to meters. And that seems annoying, but we will practice that in class, and I will show you that 0.02 meters equals 2 centimeters. Hopefully that's the right math. I just did that in my head. That's wrong. It's 200 centimeters. Excuse me. So 0.02 meters equals 200 centimeters. Same thing. I'm saying the exact same measurement, but just differently. And I'll show you this when I talk about volume as well. Volume is the amount of space occupied by a sample of matter. So in solids, this is really easy to measure. If I have a solid, like if I have a desk, I can easily measure that volume. Length times width times height. Very straightforward stuff. And units for that is the meter squared. But for liquids, that's not so easy. So we use what's known as the liter or the milliliter. The base unit for that is the liter. And believe it or not, 1 centimeter cubed equals 1 milliliter. So there is a good conversion factor between that. I will not do that to you. That's something that just confuses my brain. So I'm not going to do it to you. But you should definitely know that a liter or liquid is measured in liters, and that's the volume of that. Mass and weight. Why is that important and why are they different? Mass and weight. Mass is the amount of matter an object contains. So we actually measure this using the base unit, the kilogram, also known as 1,000 grams. So the amount of matter an object contains does not take into account any force. So your mass is actually different than your weight. Okay? Weight is based off location. And it's all based off the measure of force that is equal to the gravitational pull on an object. So here on Earth, we have a specific weight. On the moon, we would have a different weight. We'd actually weigh a sixth less on the moon than we do here because gravity doesn't affect you as much, or excuse me, gravity is not as strong on the moon as it is here on Earth. So you really do need to know the difference between the two. We will not measure mass in this class. We will not be measuring weight in this class. We'll be measuring mass. So weight accounts for force due to gravity. And when you find weight, you actually multiply the mass times gravity. In comparison to just the mass, we're only measuring the amount of matter occupied. Temperature, this is not on the slide, but I'm going to go ahead and just mention one thing, is the measure of the average kinetic energy of the particles in matter. So kinetic energy, as kinetic energy increases, you start to feel something known as heat. So kinetic energy, or the energy of particles moving really, really fast, as that increases, you'll notice a temperature change. As that slows, the kinetic energy slows down, you'll notice the temperature change going in the opposite direction. We will talk about this in class. It's pretty obvious when you see it. Like if you see a pot of water boiling, you know you're ready to put your noodles in so that they can soften up. If there are any questions, please make sure to ask me on Edpuzzle. I know I've talked about a lot of things. We will be using the system of measurement the entire year, so I will not move past this unit until I feel comfortable that everybody is able to distinguish between the metric units and how to convert in between that table. Again, ask me questions on Edpuzzle. Hey, wait, I lied. There is a what's it called on here, a temperature slide on here. I'll just talk about it in class. I didn't really know what I was talking about, I guess, when I said I didn't have a slide. Either way, ask me questions on Edpuzzle.